In this presentation I'm going to show how one constructs matrix representations of the angular momentum operators. So we've already seen that we can define angular momentum eigenfunctions which have the property that they're simultaneous eigenfunctions of the L squared operator with eigenvalue h bar squared L plus 1, and also of the Lz operator, the angular momentum along the z-axis, with eigenvalue h bar ml. As discussed last time, the values of L include 0, 1, 2 going up to infinity, and the values of ml depend on the values of L. They go from plus L counting down in steps of 1 to minus L, which comprises 2L plus 1 values in general. And we've also seen that the sets of eigenfunctions ket L ml are orthonormal, which we can write using Dirac notation, that the bracket between two states with different values of either L or ml is 0. Or in general, we can write the orthonormality in Dirac notation using these two Kronecker delta symbols, which indicate that the bracket between two different states is 1 if all the quantum numbers are the same, and 0 if any of them are different. Now we can use this property to construct a matrix which represents any particular operator, any angular momentum operator. Let's take the example where we want the matrix representation of the operator Lz using the set of states with L equals to 1. So there are 3 such states with ml given by plus 1, 0, minus 1. And the way it's done is to construct a matrix, in this case with L equals 1, since there are 3 values of ml. The matrix we would have is a 3 by 3 matrix, which represents the operator Lz. So everything the operator Lz does, its commutation properties, its eigenstates and so on, are also properties of the same matrix. So we can label the rows of the matrix by the bras. So we have 3 bra states, each with L as 1, so that's the first index there, and with 3 different values of ml. And we can label the columns of the matrix, the vertical columns, with the 3 ket states, again with the index 1 representing the value of L, and the second quantum number being the value of ml. So we have 9 numbers which are elements of this matrix. If we take one example here, this particular element here is calculated by taking the bracket. In this case the row belongs to the ket 1 minus 1, so that's the ket, the operator Lz, and the ket state which belongs to the column, so this would be 1 plus 1 in this case. So that's the Dirac bracket in which the bra and the ket sandwich the operator. Now we can use the eigen equations to evaluate this element, and the way that's done is just to look at the last 2 terms in this. The ket 1 plus 1 is an eigenstate of the operator Lz with eigenvalue h bar times the ml value, which in this case is plus 1. So those last 2 terms evaluate simply to h bar times the number plus 1 times the ket. If we put that together we would get the number plus h bar and then the bracket between 1 minus 1 and the ket 1 plus 1. Now from the Kronecker delta property, from the orthonormality, we know that the bracket between 2 different states is 0. So this element evaluates to 0. And we can repeat that process for the other elements in the matrix. So if we take, for example, this element here, in this case we have the row belongs to ket 1 plus 1, we have the operator Lz, and we have the ket 1 plus 1. The ket 1 plus 1 is an eigenstate of Lz. Since the ML value is plus 1, this again is plus h bar, is times the ket 1 plus 1. And now we can evaluate the whole term as being the bracket 1 plus 1 with the ket 1 plus 1 multiplied by the number h bar. And due to orthonormality, the bracket between two identical states is 1. So the whole term evaluates to plus h bar. And we can repeat for each of the values in the matrix. And we find that for the matrix representation with L equals 1, the Lz operator should be represented by a 3 by 3 matrix given by h bar times the values of ML on the diagonal. So plus 1, 0, minus 1, with all the other elements being 0. So a diagonal matrix is one where the non-zero elements are only on the diagonal of the matrix, where the row and the column indices are the same. All the other elements are 0. And that's true for the matrix Lz, whichever angular momentum quantum number we choose. So if we have L is 2, then this time we have 5 states. But again, we have the ML values plus 2, plus 1, 0, minus 1, minus 2 on the diagonal, and zeros in all the other places. So in general, the matrix representation of the operator Lz is a 2L plus 1 times 2L plus 1 matrix with the ML values, so starting at plus L, going down L minus 1, all the way down to minus L on the diagonal, and zeros everywhere else. So that's the matrix representation of the Lz operator. Now we can make similar arguments for the L squared operator. In this case, the eigenvalues of L squared are just h bar squared L plus 1, and that's the same for all of the different ML values. So for the case L is 1, then we have 1 times 2, so this would be 2 h bar squared, and the matrix would just be, in this case, a diagonal matrix with 1s all the way along the diagonal and 0 in the other places. So again, a diagonal matrix. And the same for, similarly for L is 2. This time 5 states, this time with the eigenvalue h bar squared 2, 2 plus 1, so 3, and then a 5 by 5 matrix with 5 equal elements, this time along the diagonal, and 0 everywhere else. The factor in front evaluates to 2 times 3 is 6 h bar squared. And similarly, the L squared matrix for general L would have h bar squared L, L plus 1, and then again a 2L plus 1 times 2L plus 1 matrix with 2L plus 1 values of 1 along the diagonal and 0 everywhere else. So that's how one calculates the matrices for Lz and L squared. In the next video we'll look at the shift operators L plus and L minus and see how to construct the matrix representations of the operators Lx and Ly.